We are very happy to have you all here and join us for this first ITS seminar this fall quarter. We have our invited speaker, Professor Joseph Chow. He's an assistant professor at NYU. He's founding director of the C2 Smart Transportation Center at NYU and an NSF Career Award recipient. He holds an associate editor position for 2 transportation journals and has received the CUTC New Faculty Award in 2018. He obtained his bachelor's and master's from Cornell University and has published over 60 journal articles since he received his PhD in 2010. And as you may know, he did his PhD here at UCI under Professor Regan and Professor Jay. And after graduating, he did a postdoctoral training until 2012 with Professor Ricci and Professor Recker. So he has worked with many of our faculties here at UCI, and we're very glad to have him here and start our webinar series with him, in particular with such an interesting topic as mobility as a service and the advances made in this research area. Thank you very much, and the floor is all yours.
Okay, yeah, thanks, Irene, for inviting me and having me give a talk here. Yeah, this is a really great opportunity for me because usually I get to meet many of you at TRB in January, but with COVID right now, especially, I think just having a chance to speak with you, and I also agreed to participate in alumni networking exchange later on. So feel free to reach out to me. My door is open always to UCI students. Yeah, I'm just delighted to have a chance to share some of the work that my lab's been doing the last few years. And this work that we are doing, it's largely thanks to the education and the mentorship that I had at UCI. So it's really great for me to have a chance to kind of give back, right, to the university, to the efforts of the faculty here. So yeah, the title here is talking about mobility as a service, there has been a lot of research in the last few years at looking at this whole phenomenon of shared mobility services. So what makes my work a little bit different is I have this interest more in focusing on systems where we have multiple operators and how they interact with each other. So I think that's kind of like the key difference with what I've seen a lot of other shared mobility service researchers have been looking at. So I'll talk a little bit about that work that we've been doing, kind of giving some highlights of a few research projects that we've done, some studies, and give some kind of like an overview of the kind of the impacts that we've had from that work. So as you all know, transportation field has changed quite significantly in the last century. And this is the 2 pictures from one from interstate highway development and one from the BART development when they first started back in the 50s and 60s. And it's changed to the point where now we have a lot more disciplinary field of transportation, right? So you see here, this is a project of the Mobility on Demand Sandbox funded by the Federal Transit Administration. This is a countrywide mobility as a service program provided by in Denmark, in Denmark. And looking at these initiatives by various companies, looking at like Moss Global or Uber and Masabi or Via, right? And even in California recently, they've been looking into this integrated transportation service program. They call it Cal ITP. So there's a lot of these efforts right now worldwide to try to design and develop these systems of essentially platforms where they function to facilitate multiple operators to serve transportation needs to users, right? So it comes, so based on that, we have this concept of mobility as service, and there's different notions of what it is. So just to be clear, I provide a definition that David Hensher gave for this a few years back. Mobility as a service combines transport services from public and private transport providers through a unified gateway that creates and manages the trip, which users can pay for with a single account, right? So, and this is some recent work from his group looking at how these kind of MaaS platforms can be governed by public entities, right? So it's pretty interesting how we're going from this type of conventional service platform to one that might be more integrated between public and private uh, stakeholders, and also breaks out the roles a little bit more between platform um, owners and regulators versus these mobility operators, right? So that's with that trend, it's adding more. It's kind of like adding more cooks to the kitchen, right? So we have all these different players involved in these kind of systems. So there's a lot of interest in various groups. I already showed you some of the work that David Hensher's group has been looking at, and then in Europe, for example, there's like a critical mass from Oded Katz's group, and then in Helsinki, in Finland, there's a couple of researchers there looking at mobility as a service as well. Coming from UCI, I think we have a certain framework and mindset on looking at transportation systems. So how do the MaaS characteristics for our interests translate to characteristics for transportation systems analysis? Right. So this is the classic Mannheim, Florian, Gaugy, or MFG framework that you're probably familiar with if you've taken the courses here at the UCI. I'm assuming it's still being covered, right? So you have the idea is that this is classifying and categorizing the different components so that you're understanding what are the data needs, right, in terms of activity systems and transport systems, as well as the mechanisms in getting that data to system flows, right? So having demand procedures, performance procedures, and market equilibration. And I've in my interpretation of this, I've added some adaptations, like looking at environmental differences from one instance of one city to another. But based on this kind of framework, what are some of the characteristics of MaaS, right, that would be of interest to us? So for one, when we look at the platforms and the operators, instead of looking at a single operator or platform, now we are looking at one or more platforms, each of which might be employing or facilitating one or more operators, right? So now you're dealing with multiple transport systems, right? And they can be mixing between operators and platforms. So there's different roles there. In terms of the dynamic systems, the MaaS platforms tend to focus much more on dynamic systems that are using real-time information, real-time data, right? So right up your sleeves if you're doing a lot of research and on dynamic traffic and transportation systems. So these types of systems, essentially the capacity is much more dynamic, right? So like the vehicles are moving about over time, so their availability is changing over time, and this availability is a function of how the demand patterns are operating. So it's I call this congestible capacity. So the conventional notion of link performance functions is that you have a link cost as a function of congestion, and then you might have a capacity, like a physical capacity associated with it as well. But with congestible capacity, we're looking at the case where the capacity itself is a function of flow, and that can impact changes in capacity that will impact the choices that people make. And then a third case is dealing with the fact that conventional networks look at system changes as leader-follower types of like Stackelberg games, right? because these types of conventional networks, they tend to be more longer term planning. The changes in the system tend to be over longer time horizons. But with mass platforms, just the fact that we've seen this explosion of technology just in the last 5 years is enough evidence to show that a lot of it from the operator side is changing very rapidly in response to user demand. So it might be fair to look at it more as a simultaneous decision making for mass platforms between users and operators and how they interact. All right, so these are some of the kind of the challenges that we looked at and felt that we could make contributions to. So today's talk, I'll cover those, how some of the topics, studies that we've done to address those challenges. Right? One, to look at route choice equilibrium with congestible capacities. Second, to look at how we can modify the way we do dynamic pickup and delivery problems, so logistics models in real time that take into account the coexistence of other services like public transit. And then on the platform level, we're interested in better understanding how the market equilibrium for these kind of platforms operate, taking into consideration that there are two-sided markets with operators as sellers and travelers or users as the buyers, and they're making transactions, and you're trying to understand that how certain designs, if a public agency is the platform provider, there's the digital aspect of it in terms of like maybe they outsource a company to develop an app for them, but there's also the physical side as well, right? So these are very much cyber physical systems, these platforms, where the public agency might also be adding new roads, adding new bridges, changing the built environment, providing like transit stations and such that can really modify effectively the transaction fees, that these buyers and sellers face when they interact with each other. So we'll talk about that, and then at the end I'll provide some takeaways about this, particularly looking at collaboration opportunities that we might have in the future. So this first work is actually the newest of the work that my group's been doing. So this is a work with Bingqing Liu. She's now starting her second year as a PhD student with me, we submitted this for TRB, but we're trying to get this published in the journal now. So the motivation, what is this all about? So I took a map from New York City, Lower Manhattan area. I don't know if you guys had a chance to visit New York before, but I live near Washington Square, so like somewhere around here. That's not my exact location. I just put a location close to there. And then this location here is a potential starting point where maybe I just got out of Whole Foods and I wanted to take a city bike back to my home. And one potential path I might choose would be to go like this, right? Where those are the stations that are closest to me. But if you look at the status of those stations, you can see that this one station is pretty low on available bikes, and this one is pretty full, right, on bikes. And so that can impose risks for me when I get there and I actually use, try to find the available capacity to make use of the bikes. So in this kind of system, in this type of network, right, the bottlenecks are not necessarily along these links, right? So in traditional traffic analysis, traffic network analysis, we tend to focus the bottlenecks on congestion on the roadways where they're traveling. But in these types of mobility as a service systems, bike share is one example that can fit into that grander scheme as one of the operators. the bottlenecks are at the vehicle stations, right? The bike stations, the facilities that are providing the capacity. And these bottlenecks are also very dynamic, right? So if at that moment someone was taking a bike from here to drop off at that location, or like another person was taking a bike from here to drop it off at another location, that will change the availability pretty instantaneously, right? So that kind of impact implies that the dependency of the capacity on flow is non-separable. It's actually dependent on flow from other links in the system. And that's one thing that really complicates this problem, right? Because we're often dealing with separable link congestion functions that where the flow that impacts it is just flow on that link. But in this case, it can be much more complex. Right? So how do we deal with that? I mean, there's of course there's always the dynamic models of assignment and matching and so forth. But if we are looking at this from a planning perspective, and we wanted to just understand the steady state conditions, right, of having these kind of interdependencies on the capacity and how that impacts people's route choices, right? Like for me to choose this route versus, let's say, for me to go, take this route instead, having a model that accounts for those kind of dependencies could be important. And looking at bike share is just one example, but there, if you think about the other types of systems out there, looking at like ride hail or even connecting it with with public transit operations and so forth, there is this potential need to capture that kind of interdependency. So we took a look at route choice models, right? And we realized that if you're dealing with route choice where the utility of the route might have a component for like the link costs, and then you also have a component for the queue delay that emerges because there is binding capacity, right? This portion here, right? The queue delay from the binding capacity, effectively that's the shadow price of the capacity constraint, right? So that value is dependent on flow, and there have been methods in the past that have considered the fact that this dependency can be captured, right? So looking at a stochastic user equilibrium model would take that into account, because now all the flows would feed back into the route choice utility function. For example, Michael Bell in '95, he came out with this study where he took the SUE model from Fisk and he extended it to include that kind of queue delay, right, where there's physical capacities to take into account. And this is one model that illustrates that, right, where this is the objective function, where if you take the KKT conditions for this, you would end up with like a logit model, and it would, so it's equivalent that the optimal solution to this formulation would get you a SUE model, and this portion here is the portion that's adding in the extra, like just the travel time cost that you're trying to minimize, and then when you try to take into account the queue delay, you can take these constraints and dualize them so that, not this part, but you can dualize them into the objective such that now this is the demand constraint and this is the capacity constraint. And so this is the Lagrange multiplier corresponding to the capacity constraints of that model, right? And he has a method to solve this using column generation algorithm with kind of like a rebalancing, right, within each iteration, where he shifts the Lagrange multiplier prices along with the flows and such, so that they fit over multiple iterations. The problem is, in our case, we're dealing with a more complex SUE problem, right? So we looked at this as basically taking it from Bell's model to start off with, but we also add in this modification, right? So under a MOS-based stochastic user equilibrium, basically we are looking at a structure where there are steady state contributions between flows and capacities, right? So this is a what we're calling a system efficiency matrix along the lines of input-output modeling theory, right? Macroeconomics, that basically says for a certain output, there's contributions from different inputs that you can capture at a macroscopic level, right? So this can define the structure of your MOS network, much like how if you look at the GDP for and looking at how the productions of different industries in the U.S. Contribute to different outputs, that IO matrix for the U.S. could differ from one in Canada or another one from another country and so forth, right? So we assume that this exists, that there is like a steady state system efficiency matrix. And so our link capacity can then be modified from a constant, this was originally a constant, to become a function of, these are H are the path flows. Okay. And so, the A is the link path incidence matrix, right? So, so by doing this, you can then have capacities that are functions of the flows that could be flows from other links in the network, right? And if you then take back the Lagrangian from the earlier formulation and make that modification, you would see it over here, right? So now we have a more complicated expression to deal with. So just some high level like a discussion of the properties. So this model itself is a generalization of Bell's original model. If the F matrix goes towards like a zero matrix, it becomes Bell's original formulation. It will just have the if you go back, does it go back? No, sorry. Yeah, this is the initial capacity. So that is the fixed capacity portion. So it would just become that. And we also proved that the conditions needed for the optimum to be a SUE. And we showed that in the case, like the optimality conditions for this. The interesting thing is that Lagrange multipliers do not interpret the same way as before. So in Bell's model, when you add in that Lagrange multiplier for the capacities, that multiplier is effectively the delays, because that multiplier becomes kind of like the pricing, right? For the and those pricing, the pricing matches the amount of delay. So you can use that to measure the cost. In this case, by having higher costs, you're impacting people's choices on other routes in other links, which feed back to yourself, right? Do that F matrix. And so because of that non-separable property, these Lagrange multipliers don't relate directly, which makes it also, as an implication, it makes it harder to solve this problem, at least using the methods that were introduced earlier in the literature. Right. So for now, we've been just trying out some simple algorithms using like k-shortest path to generate solutions, to generate our choice set, to use that to feed into the SUE and basically iterate until it stabilizes. So like as an example, if we have this as our network where there are these contributions of only from adjacent links and only 0.1 So like 10% of those link flows would contribute either positively or negatively, right, depending on the direction of the flow. And you can see that by adding these contributions, you can end up with a SUE model where like this is the static capacity case as a benchmark, right? And you can see that by adding this consideration, as you generate more iterations, so we can look at this to compare, right? You can see that the capacities end up changing. So looking at the steady state capacities, that's how they get altered with these link flows instead. Right. So now we have a model that can consider route choice behavior that also includes the contributions that people are making to, from different link flows to the capacities. And so with this, you can apply it to different types of systems and try them out. We tried it on the Nguyen-Du network. It's a very convenient network to use, right? So this is looking at, again, at static capacities. You end up with, so the static capacity in this case is 800. So assume 800 capacity for every link. This is what you would get for the SUE solution. If you then perturb it to have 10% adjacent contributions, you see that now the capacities end up increasing along those locations and decreases along these. Right? So there are some places that increase, other places that decrease, and you can further perturb it and see how that impacts the performance. Right, so this is an initial effort that we're making to try to link up the route choice behavior under these kind of mobility as a service settings to that behavior to the capacities in the system over space. Are there any questions so far?
Joe, sorry, I joined a little late. Hi, Joe. Good to see you. Quick question. Do you bring in any node capacities in this, or don't you need to?
The node capacities?
Yeah.
No, so right now the node capacities
down to a link capacity issue is basically my question.
We're changing. We basically model the node capacity as virtual link capacity, right? So.
So basically, you're assuming node capacities.
Yeah, everything's at link cost, link capacity level. Yeah.
Okay, so so if there is any sort of node links, that, I mean, they'll become like movement. I mean, if there are any node capacity issues, they'll become like movement links capacity or something like that.
If they become movement link capacity.
Yeah, I mean, if there is
like turning movements,
turning movements, kind of, exactly. So I mean, in the same manner, you make the assumption that if there are node capacities, it can be translated to link capacities.
Yes. Yeah.
Okay. All right.
Yeah. Yeah, and I also see a question. You mentioned the algorithm. We use a basic, like I think I had Bing-Ting look at like a Yen's algorithm or something like that. Something very simple. So that's why we were using the Nguyen-Du network, since there's no cycling.
Yeah, that was another question that quickly came to mind. Does k-shortest path work for path generation? Is that enough?
Yeah. So we were looking at different choice set generation methods in the literature, and that seemed to be like one of the methods that people have relied on. I don't think it's like a guaranteed, right? Like but as a heuristic approach to generate.
Yeah.
So that's what we've been relying on.
Yeah, because they'll end up, I mean, very often from experience, at least from, on regular, highway problems, k-shortest path does, I mean, I threw that into Janus model, long ago, right? So it doesn't, sometimes it doesn't work, especially, I mean, the case where you get out of the freeway and come back in, and that's the next route. I mean, it's not, I don't know if that will become an issue. Again, I think,
right.
You and I probably have talked about, k-shortest sufficiently different path problem that nobody has really looked at, right? So that came to mind as you were showing it. But so far it works, is what you found.
At least for those examples. But I think we probably need a more robust algorithm in future work. So one thing we're doing right now is talking with David Watling. I've been collaborating with him on something else. So he had looked into like this bounded choice model where the choice set generation is endogenous in the model. And he was also using some kind of like a column generation approach to develop this. So we were seeing if maybe that might be something that we can use. And also looking at route choice, not just within a trip level, but at an activity scheduling level, that can also be something of interest. So those are some of the ideas that we're working with.
So, quick question.
Yeah, sure. Hey, Mike.
Good to see you. The input-output matrix, so for something like a bike share system, I'm guessing that would change if you were to increase the capacities of each one of the stations. Is that correct? And also, have you done any calibration of that for a bike share system?
So in another work with actually my previous PhD student, Susan Shu, we were doing an online version of this where we didn't equilibrate because there was no feedback at that point. But she was trying to fit it to like a small city bike region, and she was able to do that. But yeah, the dimensionality can be an issue. So like you would need to control that. Like in the case of city bike, if you have a complete graph, right? At least for like 30-minute intervals, that result in very large link sets. But if you try to manage that a little bit, I think that's doable. But yeah, if you're changing the capacity, like the initial capacities, I guess that's what you're referring to. Yeah, that could change the outcome. So I think that's the this approach is sensitive to that. So you can look at different policies. Like if the bike share system has a policy where every night they rebalance the bikes, you can try to make use of the morning distribution as an initial distribution.
I'm just thinking about the analogy to like the economy, like it doesn't have as hard of capacity constraints as like a bike share system, right? Where like that would clearly impacts an input-output relationship between each of the stations.
It's not. So the structure is kind of like I felt it was like a input-output model, but it doesn't have the same all the same outputs, right? So like it's not leading to, well, I mean, there's still like you have link flows, and the link flows are contributing to link flows in other.
Sure.
Yeah, so it's like that.
Thanks a lot.
Yeah, no problem. Okay, so I'll move on.
Well, I'm sorry, Joe. Actually, I have two quick questions.
Okay.
Sorry,
Yeah.
So first, I mean, in the objective function, I'm wondering if there's a way to incorporate the safety consideration, because I bike a lot. I don't know how safe the bike lanes are in New York City, but definitely when I choose a route, safety the first consideration. That is also my suggestion to my kids. So I'm wondering if that could be incorporated.
Yeah, definitely. So there are a lot of studies looking at biking behavior, route choice behavior that considers safety, or like the whether or not there's availability of dedicated lanes, right, for bikes. And we have actually another study right now that we did with New York City Department of Transportation to just to look at bike safety. So in that case, we were looking at people trying to predict bike counts at different locations, and the bike counts are derived also from people that might be taking last mile trips to transit stations. And so like we're looking at like multimodal route patterns, but like when they're making their route decisions, they're also considering whether or not it's safe or convenient, or whether it's flat elevation and so forth, right? So those you can capture that. I mean, in the previous slide, I was showing like a cost for that part, but you can treat it as a generalized cost that includes different.
Okay, that's very cool. And one more question, and actually you mentioned about that for the this cost function, the congestion cost function. You said a non-separable. I suppose the result. I mean, it's similar like non-separable link performance functions, and impose some numerical challenges. Actually, theoretically, we know that if it's non-separable, especially if it's non-monotone, there's no guarantee that there's a unique user equilibrium, and there's no guarantee on the stability of the user equilibrium. I'm wondering, how do you determine whether the numerical results are meaningful, or I mean, how do we choose from
that's a great
among
question.
different user equilibrium?
Yeah, so we're starting. Yeah, so when we were developing this, we were finding that that's indeed the situation. So we were identifying the conditions under which we can at least get a user equilibrium in the problem. And then as far as uniqueness, we weren't able to prove that we can get like a unique user equilibrium. So that definitely is something we'll probably need to think about a little bit more.
Yeah. Okay, cool. Thank you.
That's a really good point. Cool. So that's some of the work that we've been doing on the user side, and then on the operator side, we've published a number of studies looking at dynamic optimization for these kind of mobility networks. Looking at either like a dynamic routing or dynamic idle vehicle relocation. So one of our more recent studies is this work that was looking at combined dynamic mobility service, right, mobility on demand or ride sharing services, but looking at it in the presence of coexisting public transit services. So this is work that we did with researchers from LISER, which is the Luxembourg Institute of Socio-Economic Research. We've been collaborating with them for a few years now. So the motivation here is that we continue to see a lot of logistics models in OR literature that largely ignore the presence of other operators, right? They're just optimizing within a vacuum. They're the only decision maker, and they're providing some optimization there. But we're in the MOS setting, we're also seeing that there are opportunities to look at these optimizations, especially when we're dealing with like online context, that they can make use of the presence of other operators, because then it can provide a richer set of options, right? So for example, here, these options are basically just door-to-door service. You can make modifications to that. There are variants like VIA, they do virtual bus stops, right? So you can create collection points where people can go to be served. But in this case, when you're providing an app-based service that allows for people to choose from one of 4 different options, right? Or in fact, the system would pick the one that's the least cost, right? Then it really expands the set of options that they have available to provide a solution. Right? So like here, RTR stands for having some kind of rideshare multimodal trip with transit in both directions, access and egress. This one is where you're using rideshare for one direction, and then you're walking in the other one. And then you also, there's an option to just walk. Choose to just do rideshare only. So you have these various options, and that expands the choices available that operators can provide to users. The implications of having these kind of integrated operations is that now user paths are not just door-to-door, but they include transfers, right? So having to optimize the transfers is one of the challenges. The route cost for rideshare can go down. In fact, in our numerical experiments, I'll mention it later on, they can actually lead to transit. At the same time, you're also increasing transit ridership. But the fact that the route cost for rideshare can go down can actually have implications on the user costs because of that. So we'll talk about that. The pickups for passengers, because if they're planned earlier along the trip, right, along a multimodal trip, these pickups can be anticipated earlier as well. So that's very advantageous, especially in these kind of like online optimization algorithms. And then repositioning idle vehicles can be better supported because we have information on transit schedule and the network, so that for example, having people being dropped off at a transit station, it doesn't necessarily have to be the closest transit station. It could be one that still benefits the user while it benefits the operator. Maybe they have to pick up someone else at another location that's closer to a farther away station, right? As an example. So those considerations can be accounted for. The static version of this model is not new. So there's been work on this. This is an example from Hall. I think it's his dissertation work from like 2006 or something. So they've looked at a static version of this model where, as an example, they're making use of this transit route to make pickups and drop-offs as well as part of their delivery. But in the case of dynamic model, it's a little bit more challenging because now we have multiple decisions that we have to make, and they do not necessarily have to be made in the same decision epoch, right? So an example here, the way that we implemented this, we considered a set of epochs for the relocation decision. So it could be like every 10 minutes or something like that, or 5 minutes or more, where at the start of each interval, the system would take into, it would have an inventory of all the idle vehicles available and make a system-wide relocation policy. And at the same time, as customers are arriving, they are then being considered within a dynamic dispatch routing policy, right? So there's a mix of two different policies for this overall mobility on demand operation. And so like some of the questions that we had was how do you integrate these together properly, and how effective can they be in handling this kind of these kinds of systems. So one thing we had to do was take a prior routing algorithm that we had, where this one that we published in 2015, it's a type of approximate dynamic programming that is using a simple approximation. It's just using the queue delay as a type of cost function approximation for the cost of the decision to dispatch a vehicle to a customer. And that queue delay is approximated using an MMS. Even in reality, in reality, it's not really an MMS, but you can at least calibrate the parameters to try to improve the fit as best as you can, and it's been found effective. So with this approach, we do have to make modifications to the case with ride sharing in essentially a MOS context, right? So like now with new user arrivals, and when you're considering for each vehicle, you aren't just doing door-to-door ride share option. You're considering each of these discretely. And for the cases where you're making use of transit, you're also doing searches of local transit stations and the way that we implemented this was using insertion heuristics to incorporate that. And we then can use this along with the queue delay to make decisions about which vehicle to assign the job to transport the traveler and in what sequence. Right. So that's one of the changes. And then in the relocation aspect, we also adapted earlier work that we had done to do relocation of idle vehicles. It's also a queue-based relocation policy, which I think some of the folks at Stanford, they've been really doing a lot with queue-based approaches as well. Although in their case, they're using queuing networks, which are not facility location based, right? So there's no coverage aspect to those. So they're just looking at like networks of queues. Whereas in our case, we're actually looking at coverage, so set covering considerations. So we use a queue delay in the objective, and we linearize it in a similar way to Marinoff and Ravel's work with the maximum what do they call it? The availability location problem, the MALP. So in that case, they take the queue delay objective, which is nonlinear, and they turn it into a reliability-based piecewise linear constraint, so that as you add each additional server to that queue, it would change the cost, the requirement for the maximum intensity and such. So I won't go into like the details of those changes, but we implemented this on a small test network, and I also don't show it here due to availability of time. But we tested it on Long Island because again, you might not have visited Long Island before. New York City is over here, right? So Long Island is known for there are travelers that might commute from Long Island into New York, and they'll use this rail service called Long Island Railroad. So we felt that could be a very good opportunity to look at rideshare services that it could be very expensive to transport people from Long Island to New York City. But if they borrow, the capacity from LIRR, it could make things much more efficient, right? So we did that under various settings. So this is just showing for one of the settings where by comparing rideshare only, and if you just look at the pickups and drop-off locations, right, that's being shown, the amount of mass of the miles of transport for rideshare only compared to like when you do LIRR integrated rideshare, you save on more than half of the length of the tours of the vehicles, but you also save on journey times for the travelers. And that was one of the findings that was a little bit counterintuitive, because you would think that for travelers that have to now take, they're making transfers. So you would think that the journey time would potentially increase. But we found that this, at least in the experiment that we were conducting in the settings that we had, it was not the case, or at least it was offset by the fact that a lot of the vehicles doing the rideshare were now staying closer to those local first last mile areas, and so their availability to users was much higher. So essentially, the service rate for the rideshare services was increased due to the availability of the transit, and that reduced the user costs for wait time, and that could reduce their journey times. So that we found that was a pretty nice, interesting result from this. That this probably doesn't always happen, right? So there's certain areas, certain regions where this can really benefit. So it calls for the need to really study these better. I think there might be some questions here. I see Jay popping up here on the video. So are there any questions before?
Yes, Joe. Hi, Joe.
Yeah. Mm-hmm.
This is Ding Tong. So we've done something similar before, and we try to compare in Los Angeles area if people are using rideshare, and also they combine rideshare and transit together to complete their trips.
Yeah.
The only criteria we used before to compare these two options were travel cost. So whether they, I think we monetized did we monetize we compare whether they're gonna pay more for the rideshare. No, I think it's a travel time. Yeah, the criteria we used the word travel time was travel time. So whether they will spend more time for rideshare or they will spend more time for the two combined mode. But what we found was for the when they do transfer, especially the transfer between a transit line and a rideshare service, it takes more than we actually expect. So it makes users gonna more prefer if they have a door-to-door rideshare service than a actual transit and rideshare combined service. And how do you approach this kind of problem?
Yeah, so I think in the case if you are able to look at like a transferable utility where you convert the passenger cost into like dollars of revenue, then you can probably just look at that one cost metric. And you're saying that you found cases where the transfer delays were much higher than you anticipated.
Yes.
Yeah. So I know that we also took a look at the transit times, but in our case, we incorporated the transit schedule into this. So in like the routing, it considered that when they drop people off. So I think that was one of the differences.
So for the transit schedule you use, are they the New York Metro, or they are just a bus or something else? And what's the headway or frequency of the bus? Average
so
frequency?
I don't remember the specific headway, but this is a commuter rail, so it's the Long Island Railroad. Yeah, it's part of the Greater Metropolitan Transportation Authority, so the MTA. They also run LIRR, but yeah, it's a commuter rail. I would guess it's probably like 10-minute or 15-minute frequency during the peak periods. Yeah.
Okay, I see.
Quickly interjecting, LIRR is almost like a metro. But I mean, even though I guess it's they use commuter rails, rolling stock probably for it. But I think it's very frequent. I mean, commuter rails are like once in 2 hours and all that, right?
Yeah,
but
it's not like that. It's not like that. Yeah.
Yeah, this is fairly frequent. What I thought. Okay. So.
Yeah, so it's got a lot of capacity, and we really, this was a way for us to try to quantify, having that coexisting system, what that meant to the rideshare service, so I think that's pretty interesting.
But the time transfer is probably the most important aspect of it. You are matching it with the schedule.
Yeah, we were matching
we
the
did try
schedule.
that, I think, here too, but I don't remember how well.
I think we also added the wait time premium for the transfers as well. So like the people were weighing it higher as well. So
okay.
So yeah, those are some of the findings, and so essentially, like the reduced vehicle miles per operator for integrated service can translate into reduced user wait times. I think it depends on the setting, right? But there's such an opportunity exists. We've also incorporated into like a report we recently wrote for the FTA, and this last mile service type of work has been referenced as part of this governance toolkit by the World Economic Forum. They call it the shared electrification, automation, mobility, or something like that. The governance toolkit, and so that's something that they've been doing in parallel. And right now we have a new project start this summer where we're collaborating with VIA to really study like the micro transit market in North America. So they provided data for a couple of cities. We're using that to run simulation. I know this looks very primitive by comparison to some of the stuff that I know like JM has done. But yeah, just doing like a simulation-based assessment to provide some metrics that then we can use to do like a portfolio level evaluation across the country. So that's something that we're working on right now. Okay, any other quick questions before I move to? Do I have time? Like, how's my time on this? I know it's only 2 my time. So.
I have a question about what you said about recently. I'm Young-hoon, and I'm a second-year PhD student. You told us about the reduced waiting time, and for the integrated rideshare option, the supply can be decreased because of the decline of the demand for the reduced journey times. So are the factor of variable demand and variable supply of rideshare services considered in this scenario?
That's a very good question. So in that study, we assumed the demand was fixed. So we didn't account for variable demand. But I think it does make sense. And actually, so this study that we're doing now with VIA, we are incorporating the demand side by looking at like a day-to-day adjustment approach. So the day-to-day adjustment would be the simulating the traveler behavior, and then the within-day simulation is simulating the service provision. Yeah. So yeah, it's important. We didn't do that in that study. We're doing it in future studies.
Yes, because the impact, I mean, the reduced waiting time can is kind of somewhat cannot be realized in the real world because the demand is also changed. So the supply would also be changed because it is kind of private sector. So
yeah, yeah, that makes sense. Yeah. So in our case, we assume the fleet was just there, but yeah, like if it's Uber, they would just, you know, the pricing would change to disincentivize the drivers to locate to other locations. Yeah.
thank you.
Thanks. Okay.
So I'm Guo Liang. I have a question.
Sure. Yeah.
I noticed that the trip length decreased. The percentage of trip length decreased is different with the tour length. I want to know, how do you define the tour in your case?
Yeah. The tour length, I guess, because it's dynamic, right? It's not really like a closed tour or anything like that. It's just total number of vehicle miles traveled by the drivers, by the vehicle fleet over that period. Yeah.
Okay.
Yeah. So we're not like solving closed static tours here. So.
Okay.
So Joe, I have one question. I'm wondering if you consider if this kind of system is implemented in a large scale, so that, you know, the market penetration, you know, the percentage of these cars reach certain level, could potentially impact the congestion dynamics in a network. I'm wondering if you consider, you know, this kind of feedback loop.
That's very interesting. So we did not consider this, and in fact, yeah, that is a valid point in the case where, like in Manhattan, where it's much more congested, a bigger portion of the traffic is you know, like Ubers and Lyfts and Vias and such, right? But I think generally in our prior studies, we have kept that loop disconnected because we felt that even if there is a high volume, right, you have, I don't know, like 60,000 vehicles operating at a given moment or something, but there's still a lot of other passenger traffic outside of this consideration of the system control. So that's why we tend to not consider like a congestion effect in that way. But yeah, it would be interesting to look at larger scales to see, you know, where does this work well, where it doesn't work well. One of the topics that now I'm looking into with one of my students is service region design. So I think that topic hasn't been looked at too much, where, you know, you're defining the geofence of the border where you're, you know, that you want to operate. I think it's a problem that all operators have to face, but many of them, I mean, there hasn't. It's like a problem that's kind of overlooked. But there's a lot that we can do on the transportation modeling side, especially if we integrate, you know, demand response and things like that.
Maybe the transportation agencies, you know, traffic management centers could be really interested in this perspective. On the impacts on the overall performance of the whole system. Thank you.
Yeah, and I mean, you know, this is also evidence further that industry is interested in these kind of methods. Like Uber only recently acquired Route Match, which this is this company from Atlanta, and they're using that to provide this kind of integrated service now, to have more connection with public transit.
Yeah, because they are facing a lot of criticism.
Actually
worsening congestion.
I think just today or yesterday, the ruling was that they had to consider their drivers as employees, right? So I think that's.
In California, I mean, what's a Prop 32 or what? I forgot, or something like that.
Okay. So that will have a big consequence on the operations, and something to look at in other later.
Yeah, cool. Thank you.
how's my time? Do I have time for a third?
So it's already 11,
Okay.
but we can ask our attendants because this meeting is scheduled for 2 hours, but the announcement was, so the Zoom meeting is available for 2 hours.
Okay.
Whoever downloaded it knows it blocked 2 hours of their time, but the announcement was for 1 hour. So
yeah, I mean, I can be quicker with this one, and then we can have some questions afterwards. So yeah, so for this last topic, I'm looking more from the platform perspective, how to evaluate market equilibrium for two-sided platforms. This is work with two of my former students. Saeed is now working at Scoop Technologies with Robert Reggae, and Ted just recently moved to Texas to work with American Airlines. So the question that we're dealing with here is when you look at a network like this, the main difference now is that each of the links are colored because they're owned by a different operator. So this is a more generic representation. The link could represent like a transit operator. It could represent a trucking company. If you're looking at freight, it can represent individual mobility, like shared mobility service. So the idea here is that you're considering the route choice. Convention is that like you're looking at the route choices of travelers, but in this case, those decisions have to be also further complemented with decisions, evaluating the decisions of the operators to see that they have the incentive. And so I'll skip this since we're short on time and focus on some of the main points here. The main issue is that conventionally we use Bourdieu's principle to look at transportation systems, but this is because the transportation systems have a centralized operator or platform that's looking at at all of this. In this new context, we're looking at a platform economy, and in this platform economy, we really need to consider operators' decisions as well. So what are some of those decisions? It could be which links to serve. It could be what price to charge for accessing their network. Right? And then the platform designer can look at transaction fees. Those transaction fees can come in many different ways. So those could be like surcharges to taxi companies. It could be changing the infrastructure. There's a lot of text here, so I'm not going to dive into this, right? But there's a lot of use cases looking at like technology, incorporation, subsidies, taxing, investments, mergers between different companies, right? Whether or not a company should join in a region and so forth. Like those kind of questions, we don't really have tools to address. And so under the assumption that utility is transferable, which it could be a big question mark, right? It depends if you have the right system set up in place. But if we do have a mobility as a service platform where we have centralized credit-based, mobility credit type of system in place, it's possible that this can be much more achievable. We could model the mobility as a service platform market as an assignment game. So the conventional one-to-one assignment game, which Shapley and Shubik came up with, is basically, it's a stable matching problem, but it's one where utility is transferable. And so you have a set of buyers, you have a set of sellers, and you're trying to match them, right? So there are two sub-problems here. The main one, the first one is the matching sub-problem, which is trying to find the optimal matching between the buyers and sellers that maximizes the payoffs. And then the stable outcome sub-problem is to identify whether or not and what region of outcomes can be used to achieve that optimal matching, right? So this problem is designed for a very simple case. In our case, it's a little bit more complicated. We are dealing with a many-to-many assignment game because now user groups are traveling along user paths, which can be dictated, which can be influenced by network effects from link capacities. And at the same time, operators can own one or more operator links that might be sharing with other operators to provide those paths, right? So there's this many-to-many correspondence, which also leads to a non-uniqueness issue. There's something there too. But the link capacities, they have these this impact that's not really captured in the conventional modeling approach. And the matching subproblem is more complex, because now if you're considering which seller to, wants to, which link they want to serve, that becomes really essentially like a network design problem. I'm not going to go into the model. We don't have time, right? But basically, the modeling approach that we did was to use a multi-commodity network design problem for the matching problem, and then we derived stable outcome conditions that we can use as constraints, so that we can solve for like buyer optimal versus seller optimal, and you can then get a range. But to do so using this approach, we required initially to enumerate all the paths for like alternative paths. So like comparing to other paths along the paths that they chose. But we borrowed an algorithm from like a shortest path games literature that allowed us to, basically it involves iteratively reducing portions of the current shortest path by the operators in various sub-coalition permutations, and using the resulting paths that we generate in that context to form the kind of like the frontier, and that's much more cost-effective to do. And we show this using Sioux Falls as an example, but we also do like a smaller network example as well. But it really gives us, flexibility to look at a lot of these kind of problems like firm entry, whether or not a operator is operating under like a buyer optimal mechanism or a seller optimal mechanism, and looking at technological changes, changes in binding capacity, and so forth. So some of the insights that we found from the Sioux Falls example was that like in the base scenario, we assumed there were two operators there. One that's kind of like reflecting the this rail operator, and then the rest of the links were like more of like a local bus or private bus operator of kind, right? And then we were seeing that when we try to switch it to like a more public-oriented government rail, the objective, the intent is to make it better for the users, but that benefit gets absorbed, cannibalized by the private operator because of the nature of the trips that they're sharing multimodal trips, right? So that's an issue that needs to be considered when planning these kind of systems. And then when we looked at adding a new competitor, it can result in significant advantages to a third party. So like in this case, we looked at a scenario where we added another competing operator here. And when we did that, operator one, which is the bus operator, it benefited greatly because of the added competition between 2 and 3. And the capacity increases also can lead to nonlinear effects. So there could be thresholds where once you increase past that threshold, it will impact the performance of the market overall. So basically, this work we're looking to try to add an additional stability condition, right? Looking at that considers the decisions of the operators as well as what the route choice conditions that we've had in the past. This framework has been applied to looking at a microtransit service, Cusbus in Luxembourg. At the time when we analyzed this, we saw that this was their stable outcome space, but they were operating under here. So they were outside the stable outcome space. This is the pricing that would have been like a private taxi service. And so based on this, we concluded that their operation was not really sustainable, and indeed it's since closed down. I don't think we closed them or anything. Right? There's no feedback loop there. And we're currently also my group is currently advising New York State DOT on procuring their next statewide mobility service program. So they have like this 5-on-1 rideshare. They're looking to create a new version in the next year. So we're helping with that. And in terms of like research objectives, we're interested in integrating this the earlier congestible capacity route choice model into the user side here, so that it's not just deterministic shortest path for travelers, but it could be like a stochastic user equilibrium of users. And then another application could be to consider the assignment game in a multimodal activity scheduling context. So it's not just trip level. So those are some of the activities we've been doing. So let me conclude, and then we can, if people want to stay, they can stay. I still, my time is available, so if people want to stay longer, that's fine. So yeah, our research has been focusing a lot on like urban mobility operators. The last few years has been more on passenger transport, but I'm also currently interested in doing more urban deliveries and freight as well. I think especially in post-COVID, it's a very important topic. Some of my work has been also looking at adding optimal learning into the dynamic optimization. So the decisions in online systems is not just to provide best service, but also to best learn so that they can plan better for future service. And then also looking at these two-sided markets, multimodal activity scheduling. There's a lot of implications on these topics as well, right? Data sharing, privacy, electrification, automation. We've done work in each of those. These are some of the current grants that I'm working on. So you can see the types of topics that we're doing. We have some collaborative talks with it's Cal ITP and also the Contra Costa County with Randy Iwasaki. He's a board member for C2 Smart. I'm open to new research or entrepreneurial opportunities. So if you guys are interested, feel free to reach out to me. But if you are also interested in reaching out to other faculty or students at NYU or NYU Abu Dhabi, NYU Shanghai, and so forth, I'd be happy to make the introductions. Some of my PhD students, for some reason, they really love California. So a number of them have been going to California. So Brian, he's one of the audience member earlier. I don't know if he stayed through the whole thing. He's got a postdoc position at UCLA, but right now he's still working remotely. Shadi, who used to work with me at Ryerson, she recently got a job at Ford Mobility in the Bay Area doing new mobility models. And as I mentioned, Saeed's with Scoop Technologies. So yeah, that concludes the talk. This is my contact info. Again, feel free to reach out to me. You can email me. You can go on LinkedIn to find me. I like to just acknowledge the book because this is a work that kind of summarizes a lot of the stuff that I've been doing. That really I learned it mostly from UCI. So. And then these are the various students and collaborators on the study that I talked about earlier in this talk. And yeah, that's it. Any questions?
Yeah, Professor Chow, thanks for the presentation. I have a question on page 34.
Okay. Yeah.
Yeah, on the page 34, you say that it does not operate into the stable area. It operates out of stable area. Can you reach some kind of equilibrium, such as Nash equilibrium, in this scenario? Since Nash equilibrium is stable, but we operate in a non-stable state.
Yeah. So this non-stable state takes into account the incentives for the operators and the users, right? So in this case, it's probably suggesting it's not sufficiently incentivized for the operator because it's below the buyer optimal. When you talk about Nash equilibrium, keep in mind that the players here are not just the travelers; it's also the operators. So it does take that into account. But since we're using cooperative game theory as opposed to like non-cooperative game theory, the value functions for the in terms of like determining the stable outcomes here, it's not really looking at it as much as like in non-cooperative games you really explicitly model the dependencies of you have like best response functions and so forth where they're dependent on other decision makers. But here you're looking at you're saying there's this coalition and what are the incentives for them to be stable. So based on that we find this region. So outside of that region they don't have sufficient incentives to establish that coalition. But maybe there might be other like smaller sub-regions that might come out of this. I haven't looked into that enough to provide a clear answer about that. But at least in like the way that this is set up, we found that was problematic. Does that answer your question?
Okay, thank you. Thank you.
I have a question regarding when you have several operators and you mentioned that when there's competition among two of them, a third one would benefit. When you're talking about these benefits, are you always talking in terms of revenue? So, or also like system operation?
Yeah. So the key point here is like that we're assuming that the utility is transferable. So that means any gains made by users or operators, they can be transferred through some exchange, right? So we can use revenue because the revenue we're assuming is something that they can convert that back as like fair discounts, or it could be converted back in terms of like maybe they can ask travelers to be picked up at locations versus at some meeting point, right? In which case the cost changes for users is the access cost. So that's the flexibility here, is that we're looking at various cost elements that can convert through these. So yeah, revenue could be one measure because everything else can translate back to that. Or at least we're assuming that, which might not be the reality. Like you might have to have the technology to set up the system to allow that to happen.
Okay, thank you.
Chow, I want to ask the following question on this graph. So we are operating in a non-stable state. Is it a transitional state, or will it converge to a certain state after a certain amount of time?
Yeah, that's a good point. So here we're looking at it as a steady state, right? So we're not really looking at it as a dynamic system. I guess there could be questions of like, well, there's two things here. One is how might this change over time, and whether or not there's an attractor there that would pull in over multiple phases to get the current state into that state. I don't think that is the case here. That's not how this is defined. The other thing is, can we intervene, right? Are there interventions that you can impose on this to move that into the stable state? So here I would actually refer you to Neda Masood. So I think she recently published something looking at perturbing unstable systems into the stable system, which that's something that I'm planning to look into next to kind of see how that can be used to design like intervention policies.
Okay, thank you, Professor.
Yeah.
There's a question from Cody on the chat. Oh. You want to read it, Cody?
Yeah.
Sure. Hi, Professor Chow. This is a great presentation. Thank you so much for the presentation. It's mostly related to the last part of the presentation. What do you think would be the role of game theory in the upcoming modeling frameworks, like the evolving mobility modeling frameworks?
Yeah, there's definitely a large role for game theory to play because we're seeing more and more decision makers getting into the mix now. So a lot of these emerging mobility systems, it's hard to look at them in isolation. Even like if you look at electric mobility, like an electric car share fleet or something, right? They also need to consider charging infrastructure, which might be planned by another entity, right? So there is some level of interaction there with different decision makers as well. But any of these mobility services, I think there is a important role to consider the interactions between those decision makers. And that's why, like, we've grown so, I mean, transportation modelers and transportation scientists, we've done a lot with some of the game theory, right? In terms of like the Nash type of equilibrium. I think there's opportunity to look at more of these other areas of game theory further in future research.
I mean,
stable matching.
Yeah, that's very informative. Just a quick follow-up sort of thing. So, how much this integration of game theory into the evolving like modeling frameworks has been explored? Can you point out like to avenues where some information is available on this?
Yeah. I mean, there's actually been a lot, and a lot of it is also from the fields where there's a lot more like private sector involvement. So when you look at airlines and freight, there's a lot of game theoretic work in there. So I would suggest looking there. My previous study with Saeed Razakani, we did a pretty thorough literature review, which looked at some of the game theoretic, like network flow games, for example, where you can find some interesting problems there. And lastly, just talk to Jay. I think he's done a lot of game theory work recently too, so I think he can answer as well.
Yeah. Good. Thank you so much.
I don't know anything, Joe.
Yeah.
Hi, Joe.
Talk to Mike, actually.
Talk to Mike. Okay.
Hi, Joe.
Yeah.
Ding Tong again. So I have a bit of technical question during your presentation. You say in one of your work, you need to do the route enumeration. So I kind of have similar problem here. We also need to do a route enumeration with a budget constraint. And we've tried Yan's algorithm, and also I wrote my own algorithm for that. But except for Yan's algorithm and column generation, do you have any other thing in your mind that you think could solve this efficiently? Because Yan's algorithm, basically, if you add a budget constraint over there, you do k shortest path and you set the limit for the budget. You have to go until the budget then stop. So, and also so for other algorithms I checked, usually their complexity goes up to n factorial. So yeah.
Okay. I mean, so the long answer is I think we probably would need to take this offline. I'd be happy to discuss that more with you.
Yes, that's the thing. I'm now taking it to offline. So but offline definitely works for static
I
problems.
take it offline as in like we can spend more time in a separate meeting to discuss.
Okay. Sure.
Not taking the algorithm offline, only the discussion.
But because there have been various like some of the methods that we were seeing with the like k shortest path and such. We didn't need to use like if the flow the cost functions did not have that non-separable entity, you could use like some of the algorithms that were in the literature related to like column generation and such. But yeah, I think it depends on what you have. The enumerated routes that I mentioned earlier, that was related to this problem where when you're considering the stability of this path, you need to compare all the other paths to it. So it needed to enumerate all the other paths. But the shortcut that we found was that we can identify basically like the ones that are closest to it. So you don't have to exhaustively search through all of them.
So you mean what you found were the neighboring paths, right?
Yeah. So that's what we did, and that was done by iteratively forming different sub-coalitions to remove from that path set, and then we like searching again for alternative paths.
Okay, I see. Thanks.
Joe, I have a question about the second study, the Long Island case study. I apologize if someone already asked this. I had to step out and take a call. So I'm assuming that in the model, all the agents were in a sense fully controllable, and then that you could assign them to ride sharing direct or ride sharing and Long Island Railroad. So I guess first question is that, am I making the correct assumption? And second, if I am, do you think those results would hold up if you were modeling user behavior in a more detailed way?
Yeah, so yes, that's the correct assumption. So basically, the system is deciding what combination to assign to the traveler. So that what the traveler is assumed to do is they come into the app, they will book an origin and destination, and then the system will say, oh, the best choice for you is to for us to drop you off at this transit station, and you take the train for part of the way. Is that reasonable? I think it depends on how you implement it. So just like at a basic level, it probably is not very feasible to do something like that. But if you're defining bundles or packages where you can say, like, if under a certain scheme, you're providing various discounts, and they're choosing beforehand to allow to be allocated like that, then I think that could be done, right? But in our study at that point, we didn't consider costs, we didn't consider discounts and incentives. So if we did consider that, I think that could handle it.
Yeah, sadly, I'm becoming a little bit skeptical of intermodal trips. I think multimodal travel in cities is critical, but
yeah.
Some of my own research and some other research out there is suggesting that people don't love transferring from kind of MOD vehicles to transit lines.
I agree. I think it's really a big cost. And I think all this talk about multimodal trips, focusing on like having transfers within trip, I think it's kind of missing out like the bigger picture. So I think the bigger picture is also that having multiple options makes the set of travel options across the day more, having it's richer in that sense, right? So like you can get to a place by transit, just single mode, and then at that location you might make a trip by shared bike to another location. I think that's another avenue that people haven't explored that much, right? Kind of like the activity-based context of multimodal.
Yeah, I agree. And I think all those modes, hopefully they're well integrated, but maybe they're not, can provide kind of an option for some family to give up their second vehicle or give up both their vehicles or something like that.
Yeah, and one of the issues for the lack of understanding of multimodal trips, I think, is also the lack of data for that. There isn't, as far as I can tell, there isn't really a lot of like publicly available data that includes multimodal or intermodal trip links in people's routes to better understand that. I've been looking and I haven't really too much.
Yeah, I guess, I mean, the cell phone data, assuming that their algorithms do the right job of categorizing modes, but yeah, that's not publicly available either, so. Yeah.
So I think, and there's also, those the cell phone data studies, like passive GPS, that could be a potential avenue. And there's been some studies looking at like open source tools. I think Berkeley, they recently had one, and I know MIT has been commercializing theirs to sell. So like in New York, they tried to conduct a study to collect that kind of data, and they're looking to make that available. So I'm looking forward to that.
Thanks, Joe. Appreciate it.
Hey, Joe, this one. I have a kind of follow-up question to Max. And I feel, also, I think more and more, in the transportation, I feel that when we consider costs, and we can really not ignore the type of costs that might be associated with transferring, maybe comfort, the psychological anxiety. I suspect I never studied that. I mean, that's, from a personal experience point of view. On the other hand, I mean, it looks like related to the last one, you mentioned that some of the benefits actually could be absorbed by private sector, things like that. It looks like we are getting to the to this situation regarding Uber and Lyft, those private sector, they might be make a lot of money, but the drivers may not be better off, and also the system, the city may not be better off. Maybe that is the background of Prop 22. Thanks to Cody. So I'm wondering, what is your take? You've been studying on this shared mobility, this large scale problem. I'm just recently getting into this area from system point of view, to study the control problem, like a fleet size management problem. I'm really interested in, theoretically, if there's any framework to incorporate all this social level, social impacts. The impacts on the labor market, and all of these things. Including the demand side. We know that the demand, travel demand, is derived from activities, and activities actually derived from the social dynamics, right? It looks like many of our studies, if we do not consider this bigger picture, this broader context, many results won't be meaningful. Practically, theoretically, I understand there's a lot of interest, a lot of challenges, especially whenever we consider demand side. I'm wondering, what is your take on this? Or
yeah, this is a very big question, right? You mentioned the social aspect. There's also the legal aspect, and there's that's one of the challenges that Uber is facing right now. I think there's a lot more dimensions to these types of transportation services that we need to deal with. One of the specific ones that I've been looking at is just the incentive for companies to share the data, right? So for a lot of these ecosystems thrive, they need to be willing to share that data, but if they share it, there's risk for people to steal they can reverse engineer the algorithms. So it's hard to say. I think this has always persisted, right? The whole issue, the whole field of transportation has always been connected in so many ways to other complications, right? That makes this problem so challenging. Even like a lot of the innovations that came about with like the ITS and looking at like in the 90s, like some of the stuff that Jay has been has done, like a lot of that the innovations did not all get translated to practice because there's all these obstacles from other dimensions. So I think there'll still be the case. There'll be a lot of market driving these technologies, but there's also counter forces to get them to do. Looking at like autonomous vehicles, for example, I think one of the there's really like no, even now, right, there's no like a very specific range for when it will be vastly available. But there's obviously now many small cases, specific markets where they're starting to operate. Has Irvine, like, do you guys have any AV fleets or?
Yeah. We have last year this bot ride, the test program by Hyundai and the Pony AI.
Yeah,
but because of the COVID-19, they suspended this. But
I think that happened for some other places too. So, but I think it's a evolving issue, and those challenges will definitely have to be there. But if you're trying to capture like labor in the like a modeling framework, like Yafeng Yin has done some work with that.
Okay, cool. Thank you.
I haven't looked too much into it, but I think like these kind of like matching models and two-sided like platform economics might be a good framework to look at to see, because they've looked at these problems for like other two-sided markets like Airbnb and so forth, right? So maybe there's something there that can be applicable to transportation side too.
Okay, cool. Yeah, thank you.
But if I could ask, I guess, follow-up comments. make a follow-up comment, or maybe Joe may have some thoughts on this. Even to say that, I mean, what Menlong said is right, that there's all kinds of attention to what's happening to the drivers, right, in Uber systems, and everybody talks about that. Well, if you don't want to drive, don't drive. I mean, is that too much of a right-wing argument? I mean, let the market just decide this. It's a private company, all right. I mean, of course, we can have we can have regulations and all that, which makes sense. I mean, isn't this also some way of maybe getting them to unionize immediately or something? I'm not a right winger, but I'm just making a right wing argument out here. Should we let Uber and Lyft just handle it? I mean, if they it's supply and demand, right? If they can't get drivers, then they don't have an operation, so they'll have to pay what the drivers will come for.
I do think Uber and Lyft, they are making contributions to the society, but at the same time they are also imposing some costs on the society. In a sense, they are taking advantage of public resources like road capacity, and try to definitely helps people, but they are making a fortune out of it. And I think my understanding, Prop 22 is a kind of a game, or and also how they are trying to fight over the benefits that the Uber and Lyft and new technology, they are reaping from the new technology, and at the same time they are using the public sector's resources, transportation system. So I do see a point there, but of course I don't have a solution. I don't I don't have any stance on this. Let people decide. I mean, even if it's yes, I don't know the direction, if it's yes or no. But the fight will be, there will be more fights in the future. I do think, I think this is related to transportation research too, more and more, especially if we get to the demand side and like induced demand. We've been talking about this all the time, but there's no good model for this, because I think that's too complicated, as you mentioned. I mean, this does involve all other stakeholders. But I think from a transportation research point of view, it looks like, I mean, we cannot really ignore these issues. But of course, that calls for kind of maybe very fundamental changes in the modeling framework and in all those things in order to address this issue. Otherwise, if we just stay within the traditional transportation domain, we just talk about demand, supply, I mean, ignore induced demand in a sense, then I feel that many of the results, many of the methods cannot be really practically relevant. I mean, like Google, I mean, as Joe cited Jay's work on the ATIS. But it looks like when Google and they enter the market, they just did in their own way. But I do see the best way is to integrate these two worlds. I mean, but I mean, I don't like Google Map navigation. They just purely depend on the algorithm without considering the human behavior. Like they would route me to local streets. I don't want to do that. I just want to stay on 405. You get what I mean? I mean, even though it might be save me 5 minutes, who knows? I mean, may not save 5 minutes in the end. Anyways, I just want to stay on the route that I really like. So I do feel that there's room to integrate, combine what we have in the transportation and other areas, either but I feel that it is time. I mean, we cannot just focus on transportation anymore. I mean, we need to look at activity that has been done, but activity is not the end either. I mean, there's a lot of even bigger social background to that.
I think it calls for more collaboration with people from other disciplines, right? So like labor.
No, can I just make a quick comment there? Both Wenlong and Joe, both of you made great comments there. Wenlong, one of the things that you mentioned is we need to go beyond what we do. Both of you said that. And earlier, I think Joe was making an important comment on that. On game theory, that the private sector does a lot more of that. And you look at transportation, we actually don't do game theory because we try to. I mean, Christian Cortes and I did some work way back, 2004 or something, for the Tristan conference, which was about transit systems being looked at as a control problem, right? And it was about predicting what the dispatcher would do, and we threw that into a logic model for predicting what the dispatcher does, right? We threw that into the transit system with that high coverage point-to-point transit work. But we were still not looking at it as a game problem. We were still looking at it as a predictable problem of making models. But I think the industry does not even try to really make models. They make models of responding, right? They don't try to predict what the other company does. So anyway, that's more in the game direction. So what Joe said was absolutely right, that there's a lot more work on game theory in the private sector, business schools and all that. So I think we need to bring those things into our transportation research. In our modeling frameworks, we need to throw in how industry operates. We just cannot get away from there. And bring in the regulations that will handle the checks and balances that we need as a society, right? To handle the concerns that Wenlong had. I mean, so if the society needs to handle these concerns properly, then we need to get a handle on how the industry will do things. So I think our modeling frameworks now need to bring in the private sector. We always stayed away from it. We need to. Yeah. I think that's the bottom line, I think.
Yeah.
Just some
thoughts. Yeah, but I think there's opportunities too from like private sector. They're slowly engaging with academics and do various.
I have a feeling that it's kind of disconnected in a sense. Like Google, like this, IT, even Uber. I know Uber, they are hiring more from the transportation, sector. I feel the traditional transportation research is kind of, disconnected. One side on the new technology. It looks like we are doing a lot of our things, but Google, Uber, they are doing their own things. On the other hand, it's kind of disconnected from the society without, considering sufficiently the cause, the social cause, and those kind of things. I don't have any idea, but you've been doing fantastic work and moving towards that direction. So thanks for your insights on that.
Yeah, thanks. I think these private companies, at least they're putting the appearance of trying to reach out to public and understanding social aspects. Like they have roles in these companies for like government liaison or whatnot. They're trying to understand the public needs a little bit better. But yeah, I think ultimately looking at these platforms, they need to have public governance to really work for the community. So yeah, well, I guess that's it. Like there's I just recently watched this Netflix documentary, Social Dilemma, and talking about the disasters of social media and how it's certain things.
Right.
Yeah, and that can happen with mobility, right? If you let the streets run amok with self-driving cars that get paid to take you to like a McDonald's or something every time you want to go somewhere. Yeah.
No, I think there could be politics connected to different types of autonomous vehicles or different fleets or different companies.
Totally.
And, social media just suddenly starts saying, "Oh, that company's autonomous vehicles all have a virus in it." What's going on during the election can happen within transport. I think there's one more question from Seaway, by the way. Technical question.
Yen's algorithm does. Oh, I'm not sure. We didn't really look into Epstein's case short path.
Yeah, Epstein. That's Don Epstein from UCI actually. From his algorithm is, I believe, probably one of the best. Yeah.
Okay.
Thank you.
Cool. Yeah. Thank you. So yeah, I totally think that in the future, it looks like there's a possibility that those autonomous vehicles can drive, or not drive or whatever, drive the human drivers out of the roadway, or they are taking, they are occupying all the roads. Just like in a sense, Uber and Lyft, they are trying kind of occupying the the downtown area, things like that. I do believe some regulations are needed, and the system level understanding is needed. I mean, why they are increasing the congestion? I mean, with the increasing congestion, then the people will be forced out of their own car. Then we have to pay more. Things like that, and they can even manufacture the artificial congestion. Like they pour more vehicles on the road and increase congestion, and then increase the fare and things like that. And I do believe that, I mean, like Google and the same thing. I mean, this social media, they are, in a sense, they are collecting a lot of public, a lot of like transportation traffic information. That should be kind of the public knowledge or public, you should belong to the public, but they are making money out of it. So there's a lot of challenging in that sense. I believe transportation would be one.
Wait for the politics that will develop when we have cars becoming a society by themselves. Okay, this is Eduardo's PhD proposal actually included this. I don't know if Eduardo is around. Yeah, which is this whole idea that every car basically has a life, and it will create its own offspring, autonomous vehicles and all that in the future, right? So cars could be a part of the society by themselves, and they decide what they should do, which company they should work for, etc. I mean, they could become like every vehicle could be a part of the society, with their own individuality. I think about that.
Yeah, that's
I don't know if Joe has any thoughts on this. Maybe Joe and I have talked about
you mentioned it to me at the TRB reception last time. And I think I mean, that's a very interesting idea. Like but one of the challenges might be like if you have this hive mind mentality and you have multiple vehicles, they start acting as one. Like, how do you deal with that?
Yeah.
Maybe
Elon Musk will try decide to own the roads in Los Angeles. He just poured a lot of Tesla onto the roads. He is capable of doing that.
Yeah.
Did they end up building a tunnel in LA?
Oh, they did.
They did.
Yeah, they did.
Yeah.
Wow.
Okay, cool. That's great.
Okay, yeah, it was really great seeing all of you, and thanks again for inviting me.
Okay, thank you, Joe.
Great talk. Nice to see you.
Great talk. Great discussion.
Thank you so much.
Okay, thanks.
Have a nice weekend to all of you.
All right, bye.
Bye.
Yeah, thank you, the organizers.